Right, this is the 2012 exam, probability exam. Question 1. Nutty snack bars produced. Weights are normally distributed, so if we highlight that, normally distributed, there's a mean, and we've got a standard deviation of 0.8 as well. And the first question says, what is the probability that a nut bar weighs between 41 and 42.2? So mean of 41, standard deviation of 0.8. Well, the probability it weighs between 41 and 42.2. So that's that area in there. We'll let x stand for the weights along the x-axis. So we want the probability that x is between 41 and 42.2. So we jump over to our calculator. Going into the stat menu, we want distribution, normal, NCD. An older model calculator, but should still work. 41, 42.2. Standard deviation was 0.8, and the mean was 41. Gives me a probability of 0.4332 to 4 sig fig. Right, part B. This time notice it says what percentage. So once we've got our probability, we're going to have to times by 100 to make a percentage. So make sure you look out for that in the question. Weigh more than 42. So we want the probability that the weight, x is all the weights along here, is greater than 42. Back over onto our calculator. We've got a lower bound of 42. We want a very big number for the upper bound. Answer is 0.10564, and we're timesing by 100 to make it a percentage. So 10.6% to 1 decimal place. Right, between what weights will the middle 60%? So the important words here are middle 60%. And what weights? So it's actually an inverse problem because we're given an area, the middle 60%, which would be in there. And we want to go backwards and find these values here. So I can see that this is an inverse problem. Let's see what we do in the calculator. Distribution, normal, inverse, tail. So it's a central area is 0.6. Everything else is the same. So it's given us two values. One of them is 40.3 and the other one is 41.7 grams, and they're all to 1 decimal place. So just checking, 40.3, 41.7. Right, this time we have a number, 18,000. We're looking for an expected number. This is like a how many question. How many would weigh less than 40 grams? So we want the probability that a weights along this bottom axis is less than 40. Once I've got my answer, I'm going to times it by 18,000. It's an expected value question. Expected value, we need a probability times the number of trials, which in this case is 18,000. Right, the probability of being less than 40. So lower bound, very small number. Everything else is the same. We get 0.1056. We're multiplying that by 18,000. You get a value of 1901.682. We clearly need to round because we're talking about a number of bars. So approximately 1902 bars. Right. Stated weight is 40. theoretically they want 96 of the bars produced would weigh at least 40. What evidence do we have to support that? So what we want to happen is we want the probability of a bar weighing more than 40, the stated weight, we want that to be 96%. So let's actually check what it really is on this machine that's been set up and find the probability of a weight being greater than 40 for this machine as it stands at the moment. We get 0.894. So currently only 89% of bars weigh more than 40 grams. So the machine is not set up correctly. It's not enough. Obviously, if it claims 40 grams on the bar and you get one of these bars down here that weighs less than that, you're going to be a bit upset about that. And there's an 11% chance actually that you'll get a bar that weighs less than it should do. Right, we can reset it. So we want to reset it so that 96% of bars weigh more than 40 by changing either the mean or the standard deviation. I'll change the mean. We'll keep the standard deviation at 0.8 and let's try and work out what the mean should be to ensure that we get this happening here. So it's like an inverse problem, except that we're looking for the mean. And when we go into inverse, it's a right tail with an area of 0.96. Standard deviation is staying the same. The problem is our mean. We don't know what mean to introduce here to have that happen. So let's set it up again, and this time we'll use a mean of 0 and standard deviation of 1. So we're using the standard normal curve, the Z curve. This curve has the weights. This is the standard normal curve that all other curves come from. We need to find the value down here. So this time we have a standard deviation of 1 and a mean of 0. And that gives me a Z value down here of negative 1.75. Right, to get from any curve to the standard normal curve, we need a formula that will take values from any curve to the standard normal curve. So substituting in what we know, the value on the x curve is 40, standard deviation is remaining at 0.8, and the 40 corresponds to a Z value of negative 1.75. Now we're just going to use solver on the calculator to solve this, remembering we'll need brackets around that top line. You can of course use algebra. Different calculator. There's equation. So let's put in bracket x, no we don't want x, we want 40, minus the unknown divided by equals being sure to push solve, and we get a value which will be the mu, the unknown, of 41.4 grams. So we need to set a mean. So by setting mean equal to 41.4 and sigma equals to 0.8, then 96% of bars should weigh more than 40 grams. Right, one more question. 300 bars in here. She weighs each bar. Compare this distribution with what we want. So the distribution they claim to have is a normal one with a mean of 41 and a standard deviation of 0.8. We can clearly see this is not normal. In fact, it looks bimodal. So that's the first thing we'd comment on. Next thing that might be helpful is just looking at the heights of these bars. Good place to start. Check that it all adds up to 300 bars, but I'm pretty sure it does. You notice that the mean for this one was 41. If you look at where 41 is with this distribution, we've only got 30 out of 300, which would be 10% of bars weighing over 41. Whereas the machine is set up so that 50% of bars weigh more than 41. So clearly something is not working right. These bars are seriously underweight. If you have time in the exam, you could also have a go at working out the mean and the standard deviation for this. We'd need to use the midpoint of each class. If this is 38.5, that midpoint will be 38.25, 38.75. So let's assume we've got time to work out the mean and the standard deviation. You don't have to do this. Put the values along the x-axis. And so on. And up here would be the heights of the bars. Now I don't have time to put them all in, but you could put them all in. Once you've done that, you need to choose Calc, and then you need to set and make sure that the frequency is list 2. Oops, we did that wrong. That one needs to be list 1, but the one below it needs to be list 2. So now when we hit 1 var, but I only had a few values in there, so you'll need to have a go at working it out. I did it, and I found a mean of 40.1, and on the calculator it's written as sigma x, standard deviation of 0.861. So the standard deviation is not too different from what we expected, but the mean is quite a lot less. So you need to craft some sentences, and if I just jot down, we're going to mention that this is bimodal, not normal. The mean is clearly less than. And we would note that 10% of bars in the packet, or packets, are over 41 grams. And we could mention our own mean. We could mention that the spread looks rather spread out here. If you remember anything about the normal distribution, then 95% of values are supposed to lie within 2 standard deviations either side of the mean. 95%, that's most of the values, should be 2 standard deviations either side of the mean. So if you work out 41 plus 2 lots of 0.8, you get 42.6. Now that's 42.5, so that would be there. And 41 minus 2 lots of 0.8 is 39.4. That's 39.5, so that's there. So we're saying most values lie within that, but you can see there are a lot of values still below that. So we clearly haven't got what we wanted.